guys? Had trouble with stat lab since that new update?
I was on it this morning. It wasn't.
Just
Last week there was some issues, like last Thursday, Wednesday, Thursday. Which is why I pushed the due date for that thing that was due Thursday. I moved it to Monday of this week, so that would be an issue. All right, so let's get started on chapter 7. The first couple sections aren't too bad, and then I'll pass back the test and we'll talk about those. All right? Okay, so chapter 7, which we only have 2 chapters left. Chapter 7 and chapter 8. All right, so there's 5 sections in chapter 7 and 5 sections in chapter 8. So there's 10 sections to cover. We have about 10 class days left, so there'll be a few days where we cover 2 sections so that we can fit everything in. But that's where we're headed, all right? So chapter 7 says, inferences based on a single sample. So in chapter 6, you know, you had to create your sampling distribution from a lot of samples, right? You know, it said the mean of your sampling distribution was such and such. Here we're going to use our sample just once, all right? We're going to have a single sample and use that single sample to make inferences rather than a lot of samples, okay? So that's what chapter 7 deals with. So I want to know something about the population. I take one sample and I try and infer from that one sample. All right? So up to this point, we've learned about populations are characterized by descriptive measures called parameters. We found that decisions about parameters are based on statistics computed from the sample. So we're really going to do the same type of thing. Really not anything new in that. All right? We're still going to try and come up with information about the population by using a sample. Discover that inferences about parameters are subject to uncertainty, and that this uncertainty is reflected in the sampling distribution of a statistic. What we're going to do today is we're actually going to attach a level of certainty to how we feel, you know, about the information that the sample's given us. All right? We'll call that certainty the confidence interval. All right? So we have so much confidence, or a certain amount of confidence, that the true mean falls within these 2 numbers. All right, that's what a confidence interval is. So where we're going, estimate a population parameter on the basis of a sample. So we're going to estimate either the mean, the proportion, if we're talking about qualitative, like success or failure. So if we're saying, and one of the examples the book gives is how many post-Iraq veterans come back with post-traumatic stress disorder. What's the proportion? Now, if you have it or not is definitely qualitative, right? You either do or you don't. So we attach a proportion to it. Then we'll use the sampling distribution of a statistic to form a confidence interval. So this confidence interval tells us how uncertain we are, or how certain we are that the sample is giving us reliable data to infer about the population. And then finally, at the end of this chapter, we'll actually talk about how to select the proper sample size, which isn't something we've done, right? We've kind of waved our hand at the sample size. We've just said sufficiently large or greater than or equal to 30. In 7.5, we'll actually attach a specific number to how big the sample size needs to be to estimate a parameter, all right? And it depends on how big the population is, of course. It needs to be proportional. So that's where we're going. There we go. So 7.1. And this is just the introduction, just like the first section from all the chapters have been up to this point. All right, there's no questions for 7.1. All right, no homework assignment. So in this chapter, our goal is to estimate the value of some population parameter, whether it's the mean, the proportion of Iraq war veterans who suffer from PTSD, or the standard deviation of how long a flat screen computer monitor will last. All right, all those different types of themes. So gas mileage, flat screen, and then the proportion of Iraq war veterans with PTSD. You'll see that different techniques are used for estimating a mean or proportion depending on whether a sample contains a large or small number of measurements. All right, so is our sample large or small? The size of it, the n value. Nonetheless, our objective remains the same. We want to use the sample information to draw conclusions about the population of interest. So, whichever the parameter of interest we're talking about, maybe it's the mean, it's the average gas mileage of all cars on the road. Whatever that parameter is, we call that the target parameter. The unknown population parameter that we are interested in estimating is called the target parameter. So it's just one specific parameter, right? Whether it's the mean, the proportion, or even the variability. Right? And then to assess the reliability of the estimate. So how good is our sample in showing us what the true mean is of the population? Right? If I go and sample 10 vehicles and find out what their average gas mileage is, how confident am I that the average gas mileage of my sample is going to be the same as my gas mileage of my population? All right? Or that my gas mileage of my sample somewhere contains the gas mileage of my population. Now, of course, that sample would have to be chosen at random, right? You wouldn't want to go and just pick big jacked up V8 trucks, right, if you're looking at gas mileage. You want it to be indicative of the entire population. Often there are one or more keywords in the statement of a problem that indicate the appropriate target parameter. So anytime in the problem, if they say mean or average, they are talking about mu. Right? Of course, these are synonymous words that we've seen over and over again throughout the summer. The mean or the average is a quantitative type of data, right? It's a number. Proportion, what percentage? Now, a percentage itself is quantitative, but the reason we make proportions is to express a qualitative data, right? Percentage of male, female, right? Percentage of over 6 feet, under 6 feet. Percentage of people that live in New Mexico and are outside of New Mexico. All of those are qualitative, so that's why we say a proportion is a qualitative type of data. And then, of course, we have our spread, variance, variability. All those words mean the same, and they are quantitative values as well. So these will be the three types of parameters that we're going to try and estimate. Either the mean, the proportion, or the variance / standard deviation. Most of the time it's going to be the mean. Right? Most of the time we're going to try and construct some type of interval that will contain the mean. Right? From the examples given in the first paragraph of this section, the words mean and average imply that the target parameter is the population mean. The word proportion and proportion of Iraq war veterans with post-traumatic stress syndrome indicates the target parameter is a binomial proportion P. They either have it or they don't. Now, I'm sure there's a level of post-traumatic stress disorders. There's levels, but for the case of this book, we're going to say either success or failure. Right? They either have it or they don't. There's only two outcomes. Right? In addition to keywords, the type of data collected is indicative of the target parameter. With quantitative, you're likely to be estimating the mean or variance. With qualitative, the binomial proportion of success is likely to be the parameter of interest. Right? What percentage of Iraq war veterans have PTSD? All right, now here's some more fancy terminology. There's a point estimator, which is the value from the sample that we use to infer about the parameter. So it's the statistic that we use to tell us about the parameter. Remember, statistics come from samples. Parameters come from the population. Right? So a point estimator of a population parameter is a rule or formula that tells us how to use the sample data to calculate a single number that can be used as an estimate of the target parameter. Another way to think about that is the statistic from the sample is the point estimator. Right? Of my 10 cars that I found their average gas mileage, that would be my point estimator. For my population of all cars' gas mileage. Kind of see what's going on there? So the point estimator is the statistic. It's the sample statistic. All right, that we get from the sample. Then, and I don't use this word interval estimator. We Really, this book is the first time I've seen it. I've looked in other stats books, and they don't use that particular word, but they use this word right here, and this is the words I'm going to use. The confidence interval. Another CI is what you might see. CI is an abbreviation for confidence interval. The confidence interval is a formula that tells us how to use the sample data to calculate an interval that estimates the target parameter. So what we're going to do is we're going to create a point estimator from our sample. Say it's 10. And then I'm going to create some type of interval around 10, maybe from 8 to 12. And inside that interval from 8 to 12, I have confidence that the actual target parameter, the actual population mean, is somewhere between 8 and 12. Does that make sense what's going on there? So that interval gives us confidence that somewhere in that interval, somewhere between those two numbers, is our true population, is our population mean. Is our true mean of the population, not our true population. Everybody see what's going on there? So from the sample, I pull a point estimator, which is a statistic, and then I create some interval around that point estimator so that I have confidence that the population mean or variance, whatever the parameter is we're trying to infer about, falls within that interval. That's what it means. All right, we're going to create an interval so that we know the mean will be somewhere in that interval. The true mean of gas mileage of all the cars on the road. You know, you might be thinking, well, the wider that interval is, the more confidence you're going to have that the true mean is in it. Well, of course. Right? The bigger the interval, the more chance that our actual population mean is in that interval. Okay? So we use the point estimator is going to be the middle of the confidence interval. So we'll go a little bit above the point estimator and a little bit below the point estimator. All right? In terms of standard deviations. Okay. You can kind of see why the z-scores have been so important. Because that amount that we move above the point estimator is in terms of standard deviations, which are z-values. And the way we find the area under the curve is by using our standard normal curve, all right, our standard normal distribution. Which is why this test, I mean, out of 14 questions, what about 11 of them were just doing the standard normal distribution, interpreting z-scores and interpreting area under the curve. It's because it's so important with what we're coming up with, all right? We consider methods for estimating a population mean in 7.2 and 7.3, so we're only going to get through 7.2 today. So we're just estimating the mean of the population, all right? And then in 7.4, we estimate a population proportion, so the binomial. So we say, you know, if one NBA player or if 10 NBA players have an average free throw percentage of 74%, what's the average free throw of all NBA players? All right, that's what that's talking about, the proportion. And then finally, we'll show how to determine sample sizes necessary for reliable estimates of target parameters. And then we won't mess with 7.6. So we won't even talk about estimating the variance. All right, we're just going to go do through 7.5. Okay? So 7.2 and 7.3 is estimating the mean. 7.4 is estimating the success, right, our P. And then 7.5 is really an interesting section because it tells us how big our sample needs to be. Now, if our population is all people living in the U.S., which is what? 300 million, a little bit more, right? 320 million. A sample of 30 people probably isn't big enough, right, to draw conclusions about the entire population. But what is a big enough sample? How big does it need to be? And we'll actually answer that question in section 7.5. Okay? Back to my tuna example we've talked about a lot. Of all the tuna in the ocean, how many should we capture to get reliable data about the population? 10 or 15 or 1,000, right? What's a better number to settle at? And that's what 7.5 really talks about. Okay? So we'll create a point estimator from a sample. From that point estimator, we'll create a confidence interval that the mean of the population will fall within that interval somewhere. Okay? Here we go, 7.2. Confidence interval for a population mean, look what it says here, normal z statistic. These z-values are very, very important, right? Because here we go, we see them again right here. So consider the normal curve down here. Now the central limit theorem states that any sampling distribution, the mean of the sampling distribution will always be normal, regardless of what the shape of the population distribution is. So a 95% confidence interval, which is what we're going to see a lot, means that 95% of the area under the curve is contained within an interval. So that actually means that, 47.5% is here, and 47.5% is here, right? 47.5% is below the mean, 47.5% is above the mean. And then we don't include the tails out here. Right? You'll see why I call them tails, especially in this section. We really talk about that. So if we think back to the z-value that corresponds to 95%, or 47.5, right? 0.475 is 1.96. Remember, it wasn't exactly 2 standard deviations. The empirical rule says 68% is within 1 standard deviation, 95% is within 2 standard deviations, 99.7% is within 3 standard deviations. But when we actually went in and looked at our z-chart, it wasn't exactly 2 standard deviations, it was actually 1.96 standard deviations above, right? So 1.96 above and 1.96 below. At this value right here, I have 95% of the area under the curve that's contained within that interval. So that's where that 1.96 comes from, right? Because if we go back and look at if we go back and look here, so if it's a 95% confidence interval, half of 95% is 0.475, right? 0.95 divided by 2. So this chart, to have 95%, I need 47.5% on this side and 47.5% on this side. So we need to go find the z-value that corresponds to 0.475. And as I go through the chart right here, you'll notice right here, 0.475. When I multiply that number by 2, I get 0.95, right? 0.47 times 5. Do that in your calculator real quick if you're not sure. 0.475 times 2 is 95%. So if I have 0.475 of the area to the right of the mean and 0.475 to the left, that means I have 0.95 of the area, right? Or 95%. This number corresponds to 1.96. So that's where that 1.96 value comes from. We'll see that a lot throughout the rest of the book. That number 1.96. All right? Now this is different than the percentile. On your test, I asked you for the very last question, or the very last question of the second to last question. Right? Part D of the second to last question. Said to find a 95th percentile. You guys remember that? The 95th percentile is everything that falls below that line, where this area is 0.95 and this area is 0.05. That's the 95th percentile. The difference between a 95% confidence interval is this, right? In the middle is 95%. So 0.95 is involved in here. So this is a 95% CI, confidence interval. So if it's 95% in here, out here at the two tails has to have the same amount of area because it's symmetric. So it's going to be 0.025 here and 0.025. Right, because when I add them both together, I need to get 0.05. Does everybody see the difference between those two things? This one involves these people down here at the left tail. This one doesn't. Everybody see what's going on, what the difference is? So this z-value right here is going to be pushed farther to the left. Right? This z-value we found was 1.96. And this one is negative 1.96. But what's the z-value that corresponds to the 95th percentile? So if right here is 0, and notice how I'm calling the area inside the curve the decimal. The actual value along the horizontal axis is the z-value. And I've seen some mixing on the test. Some of you guys were, or some people were plugging in the proportion, this percentage number, for z. 0.95 is not z. Z is the value that occurs along the horizontal axis. So what is the z-value right here? Well, how much area is right here?
0.45.
Right, this is 0.45. So I need to go look for, so this whole area is 0.95, just this little area right here is 0.45. So I need to go find the z-value that corresponds to 0.45, which it didn't fall exactly, so I gave you credit whether you're on the left or the right. See it right here, 0.4495, 0.4505. So it actually occurs exactly halfway in between these two numbers, which would be 1.645 is actually what it would be. But if you did 1.64 or 1.65, I still gave you credit. So this was, so that area is 0.05 and this is 1.64. See how that z-value changed? This z-value is pulled farther to the left because I'm including this area in my 95 percentile. So what's happened is it's the same amount of area, it's just been shifted over a little bit to create my confidence interval. Everybody see what's going on there? And this is z down here. I should probably move this on top just so it doesn't mix. So all of this area is 0.95. That is not 0.25. That's 0.05. Looks like a 2. There we go. So that's the difference between the percentile and the confidence interval. Okay? Very different topics here. Because the 95th percentile means that this z-value, 95% of the area lies below it, 5% of the area lies above it. But the 95% confidence interval is 95% of the area is contained around my mean of 0, because it's a z-value, right? So that's the difference between the two. Notice the tail on the 95th is 0.05. The tails on the confidence interval has been divided in half. They're both 0.025. Okay? All right, so let's go back to 3. Okay, so that's where that 1.96 comes from. It is not the percentile, it is the confidence interval. Basically because of this right here, right? You guys still see that if I do that? So you can see the board a little better. Okay, here's the formula for the confidence interval. It's just the sample mean plus or minus 1.96, which we'll call our confidence coefficient. A coefficient is a number that appears in front of the variable. Right back when you were doing algebra and you had like 3x, 3 was the coefficient. Right? Times our sample standard deviation, where our sample standard deviation is equivalent to our population standard deviation divided by the square root of n. Right? Now, as you look at that, you notice you have to have the sample or the population standard deviation in order to answer that, which we'll have for some problems, and some other problems we'll estimate it by the sample standard deviation. Okay? So, let's look at a problem where the hospital So suppose a large hospital wants to estimate the average length of time patients remain in the hospital. Hence, the hospital's target parameter is the population mean mu, the average length of time of all patients. The way they're going to do that is they're going to take a sample of 100 randomly sampled previous patients. So they'll pull 100 files out of the drawer, 100 randomly sampled files. And they'll look at the length of stay of each of those 100 patients. All right? So that's their sample. Obviously, there's a lot more than 100 patients in the hospital over the time frame that they're considering here. All right? The sample mean X bar represents a point estimator for the population mean mu. So the average of those 100 samples will be our point estimator. All right? That'll be our sample mean. According to the CLT, the central limit theorem, the sampling distribution of the sample mean is approximately normal for large samples. Is this sample large enough to fall under? Yes, right? It was greater than or equal to 30. This one's 100. So our n value is significantly large enough. That is, we form an interval from, say that 5 times fast, we form an interval from 1.96 standard deviations below the sample mean to 1.96 standard deviations above the mean. So here's a picture of this same thing I have drawn on the board, right? And I interpret it to z values instead of x bar and mu. Because mu for z is equal to 0, right? Prior to drawing the sample, what are the chances that this interval will enclose mu? So we'll somewhere in this interval. So I'm going to find out what my sample mean is. Then I'm going to go 1.96 standard deviations above it and 1.9 standard deviations below it. What are my chances that within that interval, the actual average length of stay of all patients is contained within that interval? Well, I'm actually 95% sure. So to answer this question, refer to figure 7.1. If the 100 measurements yield a value of x bar that falls between the two lines on either side of mu, i.e. within 1.96 standard deviations, then the interval x bar plus or minus 1.96 times our sample standard deviation will contain mu. If x bar falls outside these boundaries, the interval x bar plus or minus 1.96 times the sample standard deviation will not contain mu. From section 6.3, we know the area under the normal curve between these two boundaries is exactly 0.95. Thus, the interval x bar plus or minus 1.96 times the sample standard deviation will contain mu with a probability equal to 0.95. All right, so that's a bunch of fancy general talk. Let's look at a specific example. So let's actually construct the interval. Consider the large hospital that wants to estimate the average length of stay of its patients. So it wants to estimate a parameter, mu. The population is all patients that stay in the hospital. It's going to randomly sample 100 of its patients and finds the sample mean length of stay is x bar equals 4.5. So of those 100 patients, the average length of stay was 4.5 days. Now, if those patients were selected completely at random, we can have a pretty good idea that the true mean, the average of all patients, is going to be right around 4.5 days. But how confident are we? Well, we're going to create an interval so that we could be 95% confident that the true mean is in between those two values. Also, suppose it is known that the standard deviation of the length of stay for all hospital patients is sigma equals 4. This is usually not information that we know. I mean, if we don't know the average stay of all patients, how the heck are we going to know the average standard deviation of all patients? So for this problem, we're just going to assume we know sigma. In the future, we'll actually create our sample standard deviation from these 100 people, and we'll just use that in the formula instead. All right? So we'll use our sample standard deviation, because a lot of times we don't know the population standard deviation. But in this case, for this problem, we do. Okay? That's why it says estimating the mean hospital length of stay, sigma is known. So we know the population standard deviation. So all we're doing is substituting these values into the interval. All right? So Let's do it. So x bar plus or minus 1.96 times our sample standard deviation. So this is for a 95% confidence interval, which is equal to x bar plus or minus 1.96. Remember, the formula for our sample standard deviation is the population standard deviation divided by the square root of n, right? You had to use that on your test. So I'm just going to go ahead and, instead of putting this value, I'm going to go ahead and put this, all right? So, and it's really nice when we use n values that have a perfect square, right? 100 is a perfect square. So this is equal to, so this implies the interval this is going to create is x bar minus 1.96 times sigma over square root of n, comma, x bar plus 1.96 times sigma over square root of n. So the minus is going to be our lower bound. The plus is going to be our upper bound. You guys remember doing that in 106? This confidence interval? You might not have seen it written out in this fashion. But you basically created these intervals. All right, let me put an implication. So this is in general, right? And this is the interval you can create for your homework. Just write that formula down. And I know it's not in a very good straight line, but. So let's plug in, so I know x bar, I know sigma, and I know n. Let's plug in our values for this specific example. So this implies, so my lower end, what was x bar for this case, for this problem? 4.5. So it's going to be 4.5 minus 1.96 times, what's our population standard deviation?
100.
No, the standard deviation. N is 100. 4, right. Times 4 divided by the square root of 100. Comma, 4.5 plus 1.96 times 4 over the square root of 100. So this is our 95% confidence interval in general. That's always how they will look. So do that in your calculator. So we have 4.5 minus 1.96 times 4 over 10, right? Because the square root of 100 is 10. And then 4.5 plus 1.96 times 4 over 10. Keep going. You don't have to write out every single one of these steps. I'm just doing it so we kind of know what's going on. Now the nice thing is I can type that directly into my calculator, right? I don't have to worry about order of operations for this left-hand side. So it'll be 4.5 minus 1.96 times 4 divided by 10 equals 3.716, and then do the upper one. So 4.5 plus 1.96 times 4 divided by 10. 5.284. So did everybody come up with those two values? Did anybody not come up with them? Well, kind of look at your calculator. Yeah, is that what you got? These two numbers? All right. So let's interpret what this means. What do those two values mean? It means I have 95% confidence that the population mean, or the average length of stay of all hospital patients. So I have 95% confidence that the population mean will fall between 3.716 and 5.284. And what was the unit on these?
Days.
Days. So the average length of stay of all patients, I have 95% confidence that they will be between these two numbers. Somewhere between 3.7 days and 5.3 days. That doesn't mean every patient is going to stay somewhere between those two. It means the average length of stay of all patients will fall between those two values. Now, if I want to increase my confidence, then I need to increase this coefficient, right? I need to go more standard deviations away from the mean. Because we can construct a 90% confidence interval, we can construct a 99%, we can construct an 80%, we can construct whatever size confidence interval we want, and the only thing it affects is this confidence coefficient, all right? That number will change. The x bar, sigma, and square root of n won't change, right? They're going to stay the same in the formula. So let's look at the book and read through their example. All right. So here's the exact thing I just did. So let's look at it again. Substituting x bar equals 4.5 and sigma equals 4 into the interval estimator formula, or the confidence interval formula, you get this. So here it is, 4.5 plus or minus 1.96 times 4 divided by the square root of 100. And what they do is they simplify this piece, so they figure out what 1.96 times 4 over 10 is, and they estimate it to 2 decimal places, to 0.78. So rather than go through the whole process, which either way works, all right, it doesn't matter how you do it, they get 3.72, which this rounds to 3.72, right, if I round it to 2 decimal places, and 5.28, which this rounds to 5.28 if I round it to 2 decimal places. So the interpretation is, since we know that the probability that the interval x bar plus or minus 1.96 sigma of x bar will contain mu as 0.95, we call the interval estimator a 95% confidence interval for mu. I am 95% confident that the true mean of length of stay will fall somewhere between those two values. Okay? That's what it represents. The interval x bar plus or minus 1.96 sigma of x bar in example 7.1 is called a large sample confidence interval. The term large sample refers to the sample being of significantly large size that we can apply the central limit theorem, and the normal statistic, the z statistic, to determine the form of the sampling distribution. We'll actually have to use a different statistic if our sample size isn't big enough. All right? And we'll see that. Empirical research suggests that a sample size n exceeding a value between 20 and 30 will usually yield a sampling distribution of x bar that is approximately normal. Yeah, remember looking at that one chart, where it had the population shape and they were all weird, and then as n got bigger, the sampling distribution became normal? That's what this is talking about. This result led many practitioners to adopt the rule of thumb that a sample size of n greater than or equal to 30 is required to use large sample confidence interval procedures. Keep in mind, though, that 30 is not a magical number. It's actually arbitrary. All right? That number actually changes depending on the situation. Also, note the large sample interval estimator requires knowing the value of the population standard deviation, which we usually don't. In most, if not nearly all, practical applications, however, the value of sigma will be unknown. For large samples, the fact that sigma is unknown poses only a minor problem, since we can use S to approximate it. So we can use our sample standard deviation, which is something we can find out. Right? I could find the standard deviation of my 100 patients, because that's actual data I have in front of me, right, for my sample. So here's an example where sigma is unknown. Estimating the mean hospital length of stay where we don't know sigma. So we don't know the population standard deviation, which happens more often than actually knowing the population standard deviation. So refer to example 7.1, the problem of estimating mu, the average length of stay of a hospital's patients. The length of stay in days for the 100 sample patients are shown in table 7.1. So of all 100 patients that got pulled out of the drawer, here's the length of stay. All right? You notice there's a lot of ones. This distribution is kind of skewed right? Because there's only a few outliers. But the sample mean will be approximately normal, right? The mean of this, the average. So there's all of our days for our 100 patients. There's 100 data points here. 10 rows and 10 columns. Right? So using that data, I can find the standard deviation. The hospital almost surely does not know the true standard deviation of the population. However, since the sample size is large, we will use the sample standard deviation as an estimate. An SAS printout summary, statistics for the sample of 100 lengths of stay is shown at the top of figure 7.2, right, which is at the bottom of this page. So all they do here is they basically just substitute S for sigma. That's all they do. So here's our population. X bar plus or minus 1.96 times sigma over square root of n is approximately, so they're not saying it's exact, they're approximating, X bar plus or minus 1.96 S divided by square root of n. So they're just doing a straight substitution. Instead of sigma, they're going to use S. They're going to say that they're approximately equal. And look what we come up with for the length of stay. Dang near the same interval, right? 3.81 to 5.25. Is that going to be smaller or bigger than our other interval? Which interval is bigger, this one or that one?
That one.
This one is, right? Because it goes lower. That one, the low end is 3.81. This one, the low end is 3.71. This one, the high end is 5.28. That one, the high end is 5.25. So we have a little bit less confidence, right? It's slightly smaller, but it's not that much. That is, we estimate the mean length of stay for all hospital patients to fall within the interval 3.81 to 5.25. That's all it is. So, of course, our sample being only a sample will only give us an estimate for this, right? So this is actually a little bit smaller than if we had the population standard deviation. Because our population was 4, right? This one's 3.68. That one's smaller. And then here's our SAS printout. All right. And we'll see this T statistic. We'll see that coming up. That's what we use when we have smaller sample sizes. And then we'll see this DF coming up, right? Stands for degrees of freedom. So there's our mean, our standard deviation, and look, it creates a confidence interval. A 95% confidence interval is from 3.8 to 5.26. Right? And why is this one different? Well, it's because our mean was 4.53 instead of exactly 4.5. So that's why it's slightly different than our population one. Population standard deviation confidence interval. That's basically all it is, all right? Just plug and play. We're plugging the values in and creating a confidence interval. Okay? Okay. That is due to the fact that when sigma is unknown and n is large, the sampling distribution of x bar will deviate slightly from the normal z distribution. In practice, these differences can be ignored. Right, so let's look at a couple more definitions. 947. Can we be sure that mu, the true mean, the actual mean of the entire population, right, of all lengths of stay, is the interval from 3.81 to 5.25 in example 7.2? We cannot be certain, but we can be reasonably confident that it is. This confidence is derived from the knowledge that if we were to draw repeated random samples of 100 measurements from this population and we form the interval x bar plus or minus 1.96 sigma each time, 95% of the intervals would contain mu. So however many samples I take, all right, we were to draw repeated random samples. So of all the random samples, 95% of the intervals I construct will contain mu. That's what this is saying. Right? We have no way of knowing whether our sample interval is one of the 95% that contain mu or one of the 5% that do not. But the odds certainly favor it containing mu. Right? I'd bet on 95 before I'd bet on 5%. So there is a chance that we have an interval that's the 5% that actually doesn't contain mu, right? That's the 5% of all possible intervals that doesn't contain mu. But most likely we do. The probability 0.95 that measures the confidence we can place in the interval estimate is called a confidence coefficient. The percentage, 95%, is called a confidence level. So the confidence coefficient is the probability associated with the confidence level. Right? The confidence coefficient is the probability that an interval estimator encloses the population parameter. That is, the relative frequency with which the interval estimator encloses the population parameter when the estimator is used repeatedly, a very large number of times. The confidence level is the confidence coefficient expressed as a percentage. So whatever this value is, and on your homework it'll ask you to construct a 90% confidence interval, so the confidence coefficient would be 0.9. A 95% confidence interval would be a confidence coefficient of 0.95. And I even ask you to construct some 99% confidence intervals. All right? Where the confidence coefficient would be 0.99. So here's an example of 10 estimates, or 10 confidence intervals. So we create 10 samples, and we construct a confidence interval for each. The blue line is the confidence interval. The vertical line, mu, is the population mean. Now, not every one of these confidence intervals actually contains mu, right? We see number 4, the confidence interval we created from that sample doesn't contain mu. But 9 out of 10 do. What this is saying is, in the long run, if I took an infinite amount of samples, if I took 10, then 11, then 12, and then kept going, 100, 1,000, 10,000, of all the confidence intervals, 95% of all the blue lines would cross mu. That's what that's saying. So 95% of all my intervals would contain mu. All right? So that's another way to think about the confidence interval. Right. If our confidence level is 95%, then in the long run, 95% of our sample confidence intervals will contain mu. In this sample, this is only 10 samples. This is not in the long run, right? That's in the short run. But still, 9 out of 10, 90% of my confidence intervals contained mu. 9 out of 10. Suppose you wish to choose a confidence coefficient other than 0.95. Notice in figure 7.1 that the confidence coefficient 0.95 is equal to the total area under the sampling distribution less 0.05 of the area, which is divided equally between the two tails, which is exactly what this bottom drawing is. Right? It contains 95% with omitting 0.05% that's been divided equally between the two tails. Excuse me. Right? Using this idea, we can construct a confidence interval with any desired confidence coefficient by increasing or decreasing the area, call it alpha, assigned to the tails of the sampling distribution. So alpha is what's left over. So in this case, alpha is 0.05, right? Because it's 1 minus 0.95. Right, is alpha. So our confidence coefficient is 1 minus 0.05, that's 0.95. So alpha is what's left over. Right? Alpha is our tails. And this looks like an A. It's actually a Greek letter that means alpha. It kind of looks like, you know, the little Jesus fish that you might see drawn with the little tails. That's kind of what it looks like, without the line going down the backside right here. So the way I like to draw alpha is just by making a little like that. So there's an alpha. Right? For example, if we place the area alpha over 2 in each tail, so this is alpha over 2 because alpha is 0.05. So 0.05 over 2 is 0.025. 0.05 over 2 is 0.025. And find the z values such that alpha over 2 will lie to its right, right? Because our z chart only tells us half, right? It gives us this value. So that's why we only consider alpha over 2, because we're only looking at one of the tails instead of both of the tails. So what I want to do is, so let's look at this. For example, if we place the area alpha over 2 in each tail, and if z of alpha over 2 is the z value such that alpha over 2 will lie to its right, then the confidence interval with confidence coefficient 1 over alpha is this. So all they've done is they've replaced 1.96 with z sub alpha over 2. So that's saying what z value has half of the area to the right of it. Half of my alpha to the right of it. So let me show you using a different one. So let's create an 80% confidence interval. So what's my alpha in this case? What does alpha equal? It's the opposite, actually. Right. So it says right here. So we created a 0.8. So 1 minus alpha equals 0.8. So alpha's got to be 0.2. All right. So alpha is 0.2. So then alpha over 2 is equal to what? Point what? What's 2 divided by 2? 0.1. So what that means is in each tail, I'm going to have 0.1 of the area. So here's 0. So that's my z alpha over 2. This is negative z alpha over 2. So that means in this area I have 0.1, and in this area I have 0.1. Does everybody see that in both of the tails? And the reason I have to do this alpha over 2 is because that's how my z chart only tells me half of the curve, right? So then what's the area contained right here?
0.4.
Right, because in between those two lines is going to be 0.8, so half of it is 0.4. See why reading that z chart is so important right here? Because we need to go find a... So this is going to be the number I'm going to look for in my chart, in the body of the chart, and find a z value that corresponds to it.
That corresponds to the 0.4.
To the 0.4. Right? Because that's half, because my 80% confidence interval, this is definitely 80%, right? But my chart only tells me half. So I need to divide that in half. So I need to go look at my chart and find where 0.4 is. So let's go look at it. And it's not going to be exact, right? So we're going to have to kind of estimate it. Right here. 0.3997, and here's 0.4015. So I'm just going to go ahead and use this value. 1.28. So my z value is 1.28. Yeah, and I've seen a lot of people swapping those two things. They're swapping your area with the z. So I've seen a lot of people plugging this number into the z formula, where this is the number you plug into the z formula, right? The actual z value. So if I wanted to create an 80% confidence interval, my confidence coefficient would be 1.28. If I wanted to create a 99%, we could do that too. So let's go ahead and do that. What's a 99% confidence interval? So what's my alpha in this case? 0.01. Because what's left over, right? And the way you answer that question is you plug in alpha right, into the 1 minus alpha equals 0.99 and solve for alpha. So what's alpha over 2? 0.005. So that's going to be the area contained in both of my tails. So here's 0. So here's z alpha over 2. Here's negative z of alpha over 2. So out here is 0.005. So out here is 0.005. So what's going to be in each of these halves? Basically 0.5 minus 0.005. Right? Is going to be what's in here, which is what? 0.495. So in here is 0.495. If you can't see that, you guys are welcome to stand up and come look at it. So then in here is 0.495. So what's the z value that corresponds to 0.495? Well, I'm not even there yet. Look, there's 0.4936. 0.499, 0.4951. So it's actually going to be exactly in between those two values. So it's 2.5, what is it right here? 2.57, and it's in between 7 and 8, so it's going to be 5. So 2.575. That's the z value. And it might just have 2.58 in the book. We'll have to look at it. So my z value that corresponds to a 99% confidence interval is 2.575. I need to go 2.575 standard deviations above the mean, 2.5 standard deviations below the mean, and then I'll have 99% of the area contained in that interval. All right? But you kind of see what's going on here? You can see why I stressed the z-chart so much. Right? Because we use it over and over and over again. Remember, this is area under the curve. This is the value of the horizontal axis. What I want to do now is look. There's a nice chart in your book, 304, that actually gives us all these z values. So here it is. So if you want to construct a 90% confidence interval, the z value that corresponds with it is 1.645. A 95% confidence interval, which we've already seen, is 1.96. And the 99% confidence interval, which is the one that we just came up with, remember my z value was 2.575, and look what it is here. So alpha was 0.01, alpha over 2 is 0.005. So it's basically asking what z value has this much area to the right of it. Well, that's 2.575. Write those three confidence coefficients down. You're going to see those again on your homework. So if I ask you for a 90%, you plug this in for your confidence coefficient. Or your coefficient right here. I better be careful calling it a confidence coefficient. If it's 95% confidence interval, then you plug in 1.96. If it's 99%, you plug in 2.575. If it's 80%, you plug in 1.28. And see how as my confidence level gets smaller, my distance from the mean gets closer? Right? You guys see that? As we get farther away from the mean, my confidence grows. Because my interval is bigger. And this is how they do it for the 90%. So for the 90% confidence interval, right, if it's 90%, that means there's 45% on this side and 45% here. So if there's 45% here, that means there's 5% on the tail. Right? So I would go and find the z value that corresponds to 0.45, and it's 1.645. Okay? And then here's some formulas that you'll use. So sigma known, if sigma's known, then you use sigma in the formula. If sigma is unknown, then you just use S in the formula, or sample standard deviation, which all those values will be given to you. And the Z alpha over 2, what number you plug in here depends on what size confidence interval you're trying to create. Notice alpha is what's left in the tails. See how alpha is a very small number? Alpha is what's left over, what's outside of the interval, is a way to think about alpha. All right? It's what's outside our confidence interval. And then we have two conditions. The first one, which is really the most important, the sample has to be selected at random. Right? If I'm selecting 100 patients, I want to make sure I'm not going through and picking patients that have had traumatic injuries. Right? Because that's not a random sample. Because not all hospital patients have had traumatic injuries. Maybe one of them had an allergic reaction. So you go in, you get some medicine, and you're good in a day or two. As opposed to breaking a hip where you're in there for months. Right? So it must be selected at random. And then the sample size must be large, i.e. n must be greater than or equal to 30. The reason this has to happen is so that we can invoke our central limit theorem. If n is less than 30, we'll have to use a different type of approximation, a different method for approximation. Okay. So let's look at one last example. So, conditions required for a valid CI for mu. First, the sample has to be selected at random, and then there must be at least 30 objects in the sample. All right? The things you select at random must be at least 30. Okay. Let's look at one more example. Then I'll pass back our exams and talk about those. So unoccupied seats on a flight. That's probably a bad thing, right? Well, that's definitely a bad thing if you're an airline. Because the more people that aren't in the seats, the less money you generate. Because it's not like it costs you less money to fly if there's 4 less people. I mean, the weight is so negligible, you still burn the same amount of fuel. You still have to pay all your employees on the flight the same. Right? So you need butts in the seats so that you can pay for the flight. I think for Southwest, if there's 100 seats on a flight, they need like 93 of them filled to break even. So the other 7 people is just profit. That's why airlines get by on what's called shoestring budgets. I mean, they barely get by. That's why there's 1 flight a day from Albuquerque to Vegas, because that's the only one they can fill. They have to fill it in order to fly, right? Or else they lose money. Because jet fuel is not cheap. Right? And paying a pilot's not cheap. Paying a flight attendant's not cheap. All right? So, unoccupied seats on flights cause airlines to lose revenue. Suppose a large airline wants to estimate its average number of unoccupied seats per flight over the past year. So on any flight, what's my average number of unoccupied seats? Then you can kind of determine how much money you're losing, right, on average. You kind of come up with a budget. To accomplish this, the records of 225 flights are randomly selected. So those 2 statements, just look at between the commas. Does that hit both of my conditions that we were just looking at? Yeah, they were randomly selected and there's more than 30. So we can use this confidence interval, all right? Test. And the number of unoccupied seats is noted for each of the sampled flights. So say on one flight there's 8 unoccupied seats, on another flight there's 3, on another flight there's 11, then there's 12, then there's 13, then there's 1. There's probably even some zeros in there, right, where no seat is unoccupied. Descriptive statistics for the data are displayed in the mini-tab figure, which is on the bottom of the page. Estimate mu, the mean number of unoccupied seats per flight during the past year using a 90% confidence interval. So if it's a 90% confidence interval, alpha is what? 0.1. So in each tail, there's half of 0.1, which is 0.05. So what z-value corresponds to basically 0.45 of the area? Right? This piece. Well, that z-value is 1.645. And you'll use these numbers a lot. The 3 I showed on that page for 90%, 95, and 99. You're going to use those numbers over and over again. All right. So there it is. So after some calculation, we find that 11.6 seats is the average left unattended or unoccupied. So 11.6 seats. I mean, if you do that per ticket, just say the ticket's $150 one way. I mean, you're looking at, right, pretty significant, 200 or 2,000 something dollars here, right, in revenue that you lose. Since we do not know the value of sigma, we're going to go ahead and find the sample standard deviation, which happens to be 4.1. So our average number of seats for that sample of 225 flights is 11.6 with a standard deviation of 4.1. So I'm just going to plug 11.6, 4.1, and 1.645 into the formula, along with my square root of n. So they do 11 plus or minus, and then when they multiply those two values and then divide by the square root of 225, you come up with 0.45. So then I take 0.45 less than 11.6 and 0.45 more than 11.6. This is actually a pretty small interval, right? It's basically one seat. That's the distance between those 2 points. So what that means is I have 90% confidence that my true average is somewhere between those two values. My true average of unoccupied seats. And you'll notice that it's going to be close to this number because our sample size was so big. Since our sample size was 225, this number is going to be a pretty good estimate of the entire population. Because when you got something that you've seen it 225 times and they've been randomly selected, you have a pretty good idea that that's going to be the average. So the average is going to be pretty close to this. How close? Well, either 0.45 below it or 0.45 seats above it. Basically half a seat in both directions. All right? So then your answer is 11.15 and 12.05. This value is verified except for rounding, but you notice if you round these to 2 decimal places, well, this one's off by just a little bit, right? That would have been 11.14. That's just a round-off issue. We stress that the confidence level for this sample, 90%, refers to the procedure used. If we were to apply that procedure repeatedly to different samples, approximately 90% of the intervals would contain the actual population mean, the average number of seats unoccupied on every flight over the past year. Although we do not know for sure whether this particular interval is one of the 90% that contain mu, or one of the 10% that don't, I would bet on 90% over 10%, so I'm going to go ahead and say that it does. I have confidence that somewhere in that interval will be the true mean. Okay? And then here's a nice interpretation of a confidence interval. And this, rather than read through it, I'm just going to pick out the points. The statement reflects our confidence in the estimation process rather than in the particular interval that is calculated from the sample data. So we might come up with an interval that does not contain the average. But our process tells us we're 90% confident that it does. There's usually no way to determine whether any particular interval is one of those which contain mu or one that does not. However, unlike point estimators, confidence intervals have some measure of reliability, the confidence coefficient. For that reason, they are generally preferred to point estimators. So I would rather use the interval here than just this 11.6. Right? 11.6 is my point estimator. Right? That's the statistic I got from the sample. So rather than say my average number of seats unoccupied is 11.6, I'd rather say, well, my average number of seats unoccupied is somewhere between those two values. That's what that's saying. All right? So confidence intervals are better than point estimators. Because I don't have a measure of reliability of how good this 11.6 is. The higher the sample size makes it more reliable, but I don't have a specific value I can attach to. All right? So this section really isn't too bad. Once you understand how to construct your coefficient, right? Your 1.96 and right? Once you know where these values come from. Remember, this is the z value. So this is our 95, that's our 90, that's our 99. This is actually our 80% confidence interval, right? Didn't we come up with that number? 1.28. So that's an 80% confidence interval. 0.99 is pretty close to 1, but that's actually about a 70% confidence interval. Because wasn't it at one standard deviation, there's 34% above and 34% below, which is 68%? But this actually rounded, it's actually about 0.99 is basically a 70% confidence interval. So notice as my measure of confidence goes up, this value gets bigger. 70%, 80%, 90%, 95%, 99%. Okay? All right. So let's go look at a homework assignment. Course tools. Okay, so here's what we have left for the semester. Or for the summer, I should say. We have Chapter 7, which has 4 sections we're going to cover, because 7.1 didn't have any questions associated with it. And then we have Chapter 8. 8.1, 8.2, and 8.3 will go together. 8.4, 8.5, and 8.6. So 4, 5, 6, 7, 8, 9, 10 sections on your Exam 4. Notice the Exam 4 will be Tuesday, so that's 2 weeks from yesterday. Right? Will be Exam 4. And then, so the 21st we'll take the exam, the 22nd we'll study for the final, and then the 23rd we'll take the final. Okay? So we're getting pretty close to the end. So tomorrow I'm hoping to be able to cover 7.3 and 7.4, because notice I have both of them due Monday at midnight. So let's go look at a couple questions in 7.2. And your first question always deals with the definition. Right? With a large sample confidence interval, be valid if the population for which the sample is taken is not normally distributed. You need to answer that question. But here's an example from your homework. So, a random sample of 92 observations produced a mean of 25.5 and a standard deviation of 2.5. You need to construct 3 confidence intervals. So basically, you're going to plug this stuff into the formula. Here you're going to use 1.96. Here you're going to use 1.645. And here you're going to use 2.575, right? Is that what it was? But your x bar, your s, and your n aren't going to change. The only thing that's going to change is that z alpha over 2. Because here alpha is 0.05, here alpha is 0.1, here alpha is 0.01. So all you're going to give me is the actual endpoints of the confidence interval. Everybody see that? Rounded to 2 decimal places. And I would go through the entire process and then round it at the very end. Okay? So that's your homework for this section. It'll be tomorrow by midnight. Right? Because tomorrow's the last day of the week. And there's 10 questions, but they're all just constructing confidence intervals. All right? Notice it gives you the same size confidence interval, but with a different n value. So the n value, if it gets bigger, that's going to make the denominator bigger, which is going to make, in turn, our entire interval a little bit smaller. Because if your denominator is big, your entire number is smaller. Right? Because 1 over 10 is bigger than 1 over 100. Right? So as your denominator gets big, your entire number itself gets smaller. So your confidence interval will get narrower the more n's that you have, the more observations. Your confidence interval will get closer and closer together, right? You'll be more and more confident, which is good. You want it to be as narrow as possible in a perfect world. So there's mean and standard deviation. It gives you 33.3 and 3.7. So what does respectively mean? When you see that. The mean and standard deviation of a random sample of n measurements are equal to 33.3 and 3.7 respectively. What does that mean? Not quite. That means in the order they were introduced. So see how it says mean and standard deviation, and then it gives me two numbers, 33.3 and 3.7? So the first one's the mean, and the second one's the standard deviation, because of the way they were introduced over here. See, because it doesn't say mean equals 33.3. It just says respectively. So this order is the same order as they were introduced back here. That's what respectively means. All right? And then it says, what is the effect of the width of a confidence interval of quadrupling the sample size while holding the confidence coefficient fixed? And that'll be a multiple choice answer. But that's what I was just talking about. As n gets bigger, what happens to my confidence interval? Does it get narrower or does it get bigger? Okay? All right. So let's go. So the class average for this test was the lowest of the three. It was right at 70. Which, I mean, isn't horrible, but it's a lot different than what we've had in the past. And really, I think there was just a mixing of your z value and the area. Is really the main issue that I saw. Or you were taking the area that was below z, and I was asking for the area that was above z. So it was really pretty simple mistakes, by and large. All right. So number one said, high temperature in a certain city for the month of August will follow a normal distribution. Zoom that in a little bit. With a mean value of 70 degrees. So the mean is 70. What's the area under the curve below the mean? Right? If my mean's here, how much area is below it? How much area is above it? 0.5, right? So it says, what's the probability that the high temperature on a day in August exceeds the mean? How much area is to the right of the mean? Well, half of it. So that's saying, what's the probability that z is greater than 0? Well, that would be 0.5. Half of the area. 2 says, find a value of the standard normal variable z called z naught such that the z greater than z naught is 0.7. So the area under the curve is 0.7 above it, and how much below it? And this one took a couple steps, but it's just interpreting the z-score. So it said the probability that all z values are going to be greater than or equal to z naught is 0.7. So as I draw my chart, here's 0, here's z naught. I need all of this area to be 0.7. So down here is 0.3. But my z chart gives me this area right here. What's the area right there? 0.2. So that's the value I'm looking for in my chart, is 0.2. In the body, right? And then I'm looking for the z value. So as I go through my chart and look at, and notice how there's not a positive 0.52, which might have been a little more difficult. So that's why that one wasn't written in there. So as I go through and look for 0.2, you find it somewhere between 0.52 and 0.53. And since it's down here, this is going to be negative 0.52. It's actually negative 0.525. So the z value that has 70% of the area above it is negative 0.52. Everybody see that? What's going on there? Right, because if I go and look at my, and I know it's negative because that number is greater than 0.5, so z has to be a negative value. So I go in here and look at 0.2. It's somewhere in between these two numbers. I went ahead and said, go ahead and say it's 0.52. Right? So it's going to be negative 0.52 because it's left of the mean. Because this number is greater than 0.5. But we were studying for the test. I mean, there was only really a few problems I picked out and said you have to be able to do. And they're just like this. Right? So basically, I'm asking for number 3 is pretty simple, right? I'm asking for you to just go read the chart at 2.25. So go into the chart, read it at 2.25. And pick the number out, 0.4878. How much area is contained between negative 2.25 and 0? On number 4, I've seen a lot of people answer part C. You gave me the opposite value that I was asking for. I want to know what's the probability that z is less than negative 2.3. Because 325 seconds is way down below the mean of 440. So I want to know who can run it in less than 325 seconds. So what's the area under the curve below the z value that corresponds to 325? I've seen a lot of people get the z value correct. A lot of people had negative 2.3, but then you just didn't interpret it correctly. This number is people that can run a mile in more than 325 seconds. Is 98.9%. That makes sense what's going on there? So that less than is very important. Can run the mile in less than 325 seconds. So if I was going to draw a normal curve, the very left-hand tail down there would be shaded in. Right? The very bottom of it. This one, I should have looked a little closer at it. It's not even rounded to the nearest cent. Which doesn't make a whole lot of sense here, but it's still the same answer if you plugged it in. And then I even seen a lot of people get here correctly. Because the z-value that corresponds to 0.123 of the area being above it, because I'm asking, find the price for which 12.3% of the milk vendors exceeded. So I want to find a z-value such that 12.3% of the area is above it. Right? Here's 0. So I want to find a z-naught such that this area right here is 0.123. The way I do that is 0.5 minus 0.123. And I've seen a lot of people doing this correctly. And I don't remember exactly what that was. That was the area. Was that 0.477? Is that right? .377. So this area is 0.377. So I need to go find the z-value that corresponds to 0.377. And when I go and look at my chart in the book, so go look at your chart, which value is 0.377? There's one that's exactly it. 1.16 is the z-value. So that's this number. So now I need to plug this into the z-score formula and find the x value that's 1.16 standard deviations above the mean. And if the mean is 320, then I solve this. And I've seen a lot of people set this up correctly, and then they multiply both sides by 0.1, but then you subtracted 320 instead of adding it. Or you subtracted this number. You made this a negative value, which it most obviously is not. A lot of interpreting z's. That's basically all this test was, right? Now, I didn't ask you to find the variance of a sample, like on homework 6.2. That stuff isn't nearly as important as being able to answer this type of question. You have to be able to tell me that. All right? That's very important, especially moving forward into the next 2 chapters. Okay? And really, the errors were just small. 7, 8, 9. Look at 8 and 9. Just about everybody got 8 right. Well, I think everybody did get 8 right. Some people were picking D for 9. But I was asking about the sampling distribution. So the mean is going to be equal, but the standard deviation is going to be divided by the square root of n. 500 divided by 10 is 50. Because I was asking about the sampling distribution. All right. More z-score stuff. And then here's the 95th percentile, which I kind of already talked about. Remember, it was right here that I had erased. So basically, I'm looking for the number. I'm looking for z-naught such that 0.05 of the area is above it. So that means 0.45 is below it. So notice this is the exact same number as my 90% confidence interval. And even if you just did 1.64, if this was off by a little bit, I still gave you credit. So this was the score on the exam to finish in the 95th percentile. And once again, I've seen people mixing the area with the z. So you're plugging this number into the z formula. Which you can't do. It's not correct. And then here was this one. So for 3 it says, determine the probability that the sample mean student age is greater than 25. So I want to know the probability that x bar is greater than 25, which is equal to the probability that z is greater than 2.5. Because 25 corresponds to 2.5 in terms of standard deviations. Because 25 minus 22 is 3 divided by 1.2. All right. And then I just wanted a little picture. And I've seen a lot of people giving me the population standard deviation, not the sample standard deviation. Right? I was asking you to draw the curve Draw a curve with the region described in part B shaded. Right? So I was talking about the sample mean, not the population mean. This is really all I was looking for right here. So your probability that the age is greater than 25 is only 0.0062. Basically about 1%. Okay? And I think as you go through your test, you'll kind of be like, oh, I can't believe I did that. Because a lot of them were, it wasn't really conceptual errors. It was just small errors. Plugging stuff in the wrong spot was basically the only issues that I saw. I didn't ask any questions about the uniform distribution. Right? That one, it's kind of trivial. The uniform we don't really even use anymore. It's all about the standard normal. You have to be able to use the standard normal distribution. Okay? So your homework for 7-2 is due tomorrow by midnight. So what I want you to do is go home and try it and come with questions tomorrow. And I'll have a little worksheet for us to do for it as well. I might just have us do it in class. Wait and see kind of how the questions are. Alrighty? Where's my sign-in sheet? Back over here. Oscar has it. If you haven't signed it, go ahead and put a signature on it. You guys are free to go. We'll see you tomorrow. If you have a question about your test, hang around and I'll answer them. Or if I took off too many points, let me know and I'll fix it. Remember, I'm going to let the final replace your lowest chapter test grade. So if you didn't do as well as you wanted, you can still make it up. Oh, no. Just if it's higher. Yeah.
CBC and I worked it out and searched the wrong one.
Yeah, and this was actually worth, this problem was actually worth 3 points.
Okay.
So I gave you a point, which these I was really only doing pass or fail, so I don't do that very often, give you partial points. But yeah, you had it.
I don't know what
You
I was
had it
thinking.
right there.
I circled right here because I had questioned this one, so I had circled that one for my own reference. Like, I know I'm going to get this one wrong pretty much.
Right.
I guess, I don't know what the
And I'm not sure what you were
I don't know what
filling
it
in
is.
right here. That's 1 standard deviation above. Yeah, I'm not sure what. That's 12.3% above. So what you did is 12.3% above the mean. So you looked for 0.123 in the chart and brought you down rather than the opposite. 12.3 needs to be the tail up here.
Okay.
Oh, thank you.
Oh my gosh, I feel a lot more confident on this. What is the difference between this and these right here?
Nothing.
So why am I able to do these just fine? And
Because here
with that one,
yeah, you're off by a little bit. See, I wanted 95% above. So you needed 5% over here. Which this is actually only 0.02, right? Because 2 standard deviations, within 2 standard deviations is 95%. But I wanted the 95%. So I wanted to include these down here in the 95%, which you're not doing by this picture that you're drawing.
yeah.
This is a
one right here, I didn't
95%
know.
confidence
That's
interval.
actually what we just went over.
That's the difference between percentile and confidence interval. Percentile means I'm counting this stuff down here. In a confidence interval, I don't count the 2 tails.
Okay. That percentile we're starting here.
Right. So 95%'s here and 5%'s here.
Yeah.
Okay. I knew this one. I didn't know how to figure it out. I knew it
Percentile.
was wrong. Yeah.
But yeah, no, that's good. See, you circled the wrong line.
This sample. See,
See, and then here you were
sample here.
doing, your population standard deviation instead of your sample standard deviation. Your sample standard deviation is 1.2. This needs to be your standard deviation, not 12. And you're letting 12. You're doing it for the entire population instead of the sample. And then as I read it, yeah, that's why I was trying to follow along what you had here.
Well, I think what I did is,
See, this number was way closer than this number.
but see, I did with the, I did population and sample year. But I must have got, because that number is
I mean,
not the answer.
it's close though. That's a heck of a lot closer than this one is.
Was I off by this? Did I figure that 0.5 minus?
Yeah,
this?
2.5. So your Z is 0.4798. So for 2.5, is it 0.798? .4938. So I'm not sure where you got that number from.
Oh, did I do this?
0.47.
Did I do 2.0 and go over to 5? Is that what I did?
Yep, you did 2.05, not 2.5.
Yeah.
And I think this one was worth 4. I gave you a point for that one too.
Okay.
Just small stuff, like I was saying, little bitty errors. The tediousness of it.
I just have a question.
Okay.
Because I kept getting this wrong on my homework, and so right here, like whenever I did that, like I had gotten the right answer, and then I did the 1 minus because I don't.
Well, so this is the people that fall below,
Okay.
or this is the people that run the mile in greater than 325 seconds.
Okay.
That's your proportion.
Okay.
This is your proportion that falls below 325
Okay.
seconds.
I kept getting it wrong on my homework, and then I thought about it.
And this was worth 3 points, so I gave you a point for it.
Okay.
Because you had the right value, you just didn't interpret it correctly.
Okay. And then that was stupid. I can't believe I just went fast and circled the wrong one.
Oh, dang it.
See, because I did my work, and then I just.
Normally
Just-
distributed.
And then I put 165 instead
Oh,
of
you divided that one by 10, yeah.
Well, see, I didn't even, like, I did it.
And this I was asking for the probability, not the z-score.
Okay.
So I want to know the area under the curve, not the z-value.
Yes.
This z-value corresponds to that area.
Yeah. See, I didn't even divide that one by 2. I knew that that stayed normal. See, I wrote it down, and then I just went and circled it. I didn't even look at the top one. I just saw that. It didn't even, because I divided that by 10. Because I knew that the mean stays the same whenever.
Right, right.
Yeah. See, I just circled the wrong one. That was stupid.
Oh, crap, this is actually not correct. That's actually 0, now that I look at it.
Oh.
Because you can't, if it's equal to a point, the area at a point is 0. But nobody picked 0.
Nobody picked 0 anyways. Okay.
A lot of people were picking that, and I think it's because of the way the previous one was worded.
Yeah, but
So-
I thought the same. I thought
Right.
the same thing.
Because as I look at it, that's not right, but that's okay.
And then I did the same thing right here, but I boxed that one because I wasn't sure, but you gave me points for that one. So that's the one that's greater.
Right,
than.
that's the tail.
Okay.
Right. More than 600, so you have it. This number is the area under.
Under
right?
that. Okay.
Mhm.
One
So
minus
0.4772 is this area.
Got it. And that's when you.
Right. And then here,
I just added instead of subtracted.
right, because 650, right, you should have subtracted, right, exactly. And that's why I put the minus.
Yeah. Which I understand those mistakes. I just was.
And see, you had the picture right.
I honestly did not know how to do this one until you explained it to me.
Okay.
I guessed pretty much. Well, like I drew the picture because I knew what you were asking, but I did not know how to.
How to find,
Yeah, until you explained it today.
and then it makes sense.
Yeah, and then the rest were like that one. I understand that was a stupid mistake. That one was really stupid. And then, but I was just confused of when to do the 1 minus.
So it depends on if it's the tail or if it's the inside.
Right.
That's what you always ask yourself. If it's the tail, you do the minus. If it's the inside, then you just pick that.
I did the review 4 times until I got 75% and it was like 2 o'clock in the morning.
Oh.
And it was like, that's,
Yesterday morning,
yeah.
right?
As long as I got it started, but that probably drove my grade down pretty good, right?
No, well, I think you still have like a 76 or something like that
On the,
for your overall.
oh, okay.
I'm not sure what it was before.
I didn't see.
Good, because now it's the average of